Okay, so now we're going to find out how to come up with these dimensionless variables that we were talking about. And the good thing about this is I call it cookbook here because you basically follow the steps and you can do it every time. Note that this method is only going to work for fluid mechanics. You can't use it on any other disciplines. Okay, so let's get started. First thing you got to do is list the dependent variables as a function of independent variables. So basically what we did before with lift, and that's the example we're going to use, we said that lift is probably a function of velocity, our fluid properties, rho and mu, our chord length, c, and alpha. Okay, so that's it for step one. And in real life, that's kind of a hard part, but in your problems, that'll always be given to you in one way or another. Step two, underneath each variable, you want to list the basic dimensions. Okay, we're going to list dimensions, which is the curly brace kind of thing, and that system was m equals mass, L equals length, T equals time, and theta equals temperature. Okay, those are our four basic dimensions. Okay, and really they have curly braces around them to indicate that they are actually dimensions. All right, so underneath each variable, we're going to list the basic dimensions. Now, this is a place that a lot of students mess up. It's really easy to mess up. What you probably want to do is use units to figure out what dimensions are in each variable. Okay, so for instance, so let's say down here, can use units to figure this out. Okay, so for instance, if we're doing mu's a tough one. So what you want to do for mu is go ahead and look up in the back of your book or anywhere that you have a mu value. It's going to have units next to it. One of the types of units that you come across with mu is kilogram per meter second, like that. Okay, which tells you that mu must be mass over length and also over time. And we usually will write that then as m, L to the minus 1, T to the minus 1, like that, all inside one set of braces. Okay. So same thing with lift. Lift would be newtons, which is kilograms times mass times acceleration, kilograms times meters per second squared. So kilograms is mass times meters is length per second squared, T to the minus 2. Okay. Do that for all your variables. Velocity is meters per second, LT minus 1. Rho is kilograms per meter cubed. Mass, L minus 3. Mu we just did. Mass, length minus 1, T minus 1. Chord length is just a length. And alpha is in radians. And we're going to use that as already dimensionless. Okay, so just put a line there, meaning it's already dimensionless. Okay. Step 3. So that's it for step 2. Just list out the dimensions, and you can use units to figure out those dimensions. Step 3, choose a dimension. Doesn't matter which one. So this is where your problem could vary from my solutions or from your neighbors. But it's easiest if you happen to pick one, you look at the right-hand side and pick one that doesn't have some exponents in every term, okay? Mass would be a good one here, or length would be a good one. See, I can see like a couple that don't have exponents on them. So I'm going to happen to choose M, but you could have very easily have chosen L, and you could have chosen T as well. So I'll choose M, and I'll just write L would have been just as good. And that is the dimension L, not lift. Okay, L. Okay, step 4. Now this is where you really need to understand what's going on. Okay, so this is the meat of the problem. So what we're going to do is choose a whole term on the right-hand side. Okay, sometimes right now there's just one variable in each term on the right-hand side. Eventually there's going to be a mix of variables, but right now just choose something on the right-hand side, a whole term, and it needs to contain the dimension you chose in step 3. So for us, on the right-hand side, we have rho or we have mu that has mass in it. So we're going to pick rho or mu because I had m from the previous step. Okay, so the key here is what we want to do is get rid of m in all of our terms. Okay, so get rid of m. And you're going to do it by multiplying or dividing by this rho or mu, whichever you pick, to some exponent. This whole term, whatever you pick, by multiplying or dividing the term to an exponent. To each term, to get rid of each other term, to get rid of that dimension. Okay, so what I mean, I'm going to pick rho because it's a little simpler than mu. Okay, so starting on the left-hand side, if you look at L had just a plain m in it. Okay. L had an m, rho has an m, okay, which means if I say L over rho, my m's are going to cancel out. So that's what I want to do. L over rho, and if I look at the units, L was m, L, t to the minus 2, the dimensions, and rho, 1 over rho, is going to be L cubed, m to the minus 1, right? 1 over rho is meters cubed per kilogram, okay? And look at that, the m's cancel. I did that on purpose. I divided by rho in order to make those cancel. Okay, so what I'm going to get here then is L to the 4th, L to the 4th, t to the minus 2. Left over. It's supposed to be a 2. Okay. And I need to do that with all the other variables also. So equals a function of v. Now if I look at v was L t to the minus 1. There's no mass in there, so I don't have to do anything to that. So unlike algebra, you don't have to do the same thing to every term here. You do different things to each term, and that's okay. Rho was our next term. Rho, what we're going to do is just divide by rho. Okay, and what you're going to do is always just divide that term by the one that you had picked, and what happens is that equals 1, and now you can remove this. Okay, so that's going to decrease our variables, our number of variables on the right-hand side by 1. Okay, which is good. So our next variable coming down here was mu, and mu had an m in it, okay, on the top. So in order to get rid of that m, we want to divide by rho, same as we did for L. And our mu was m, L minus 1, t minus 1. And if we divide by rho, dividing means L cubed, m minus 1. Okay, and our m's will cancel. What we have left is L squared t minus 1. Okay. Next variable was c, had no m in it, so we can leave it alone. And our last variable was alpha, already dimensionless. So when something becomes dimensionless or is already dimensionless, you just leave it alone. It stays in there. It doesn't remove like this rho does, but it stays, and it just will propagate through the rest of the problem. All right, so there we are. So let's rewrite that whole thing. So we have it, top of the page here. So L over rho, and that now has L to the 4th, t to the minus 2 dimensions, equals a function of v, which is L t to the minus 1, mu over rho, which has L squared t to the minus 1. Notice I didn't write rho, that's gone now. C was L, and our alpha is just going to keep tagging along as a non-dimensional parameter. Okay, so we've gotten rid of M. Good. What we want to do is continue that same process, get rid of all the other variables. This time I will choose L, and as my term on the right-hand side, well, C looks pretty easy, so let's go with C. Okay. So what I'm going to get over here, I want to eliminate L, and I see C just has units or dimensions of L. So I want to divide this term by C to the 4th to get rid of that L. So L over rho C to the 4th. Okay. That's going to get rid of my L. What I'm left with is t to the minus 2 equals a function of, now to get rid of L and V, again, I'm going to divide V over C. It's going to just give me t to the minus 1. Okay, you see why C is an easy one? Because it's just L. That makes it easy. Okay, mu had a L to the L squared term in it. This mu over rho had an L squared term in it. So we need to divide by C squared. So mu over rho C squared. And that is going to get rid of our L term there, and you're just left with t to the minus 1. C over C, gone, remember? Those are the ones that go away. And then we still have our alpha hanging out. Okay, so from here now, all we have left is t. We want to get rid of t. So let's look at our left-hand side. We have a t to the minus 2. We need to pick one of these terms. Okay, I'm going to happen to pick V over C. It just looks a little simpler to me. Okay, so I'm going to choose, I got to choose T because that's all we got left. And V over C is the term that I'm going to eliminate. Okay, remember it's the whole term, not just one variable at this point. The whole term on the right-hand side. Okay, so if I have T to the minus 1 for my V over C, and I have T to the minus 2 here, what I want to do is take this to the, I want to square this, right? And I want to actually take it to the 1 over this term squared in order to make that t to the minus 2 go away. So let me show you. L over rho C to the 4th. So if I invert, that one's t to the minus 2. Okay, so that's really 1 over t squared. Right? So this one is already t to the minus 1, which is 1 over t. So if I invert that, that becomes t, which is what I want, and then I want to square it. Okay, so this is what I'm trying to come up with, is a t squared, or just t squared here, right? So those are going to cancel. Okay, so to get t squared, it's 1 over, and then square it. So c squared over v squared. All right? Equals a function of v over c. That's going to go away because it's going to be v over c, gone. Okay, now we got to figure out what to do with mu over rho c. Well, this is t to the minus 1. That's the one we're using, so we can just divide. So mu c over rho c squared v is just dividing, and that's going to make it, we had t to the minus 1 times t. Okay, and then our alpha again is just going to stay. Okay, all these are now non-dimensional. So let's just simplify it a little bit. And what we have is L over rho v squared c squared equals a function of, okay, one of these c's cancels, mu over rho c v and alpha. Nice. 2 variables now. And since these are all non-dimensional, that means we're done. Done when they're all non-dimensional. Always check units. Okay, so it's easy to make a mistake along there, especially in your original set of units or when you're dividing or multiplying by something to an exponent here. So check units. It's to save yourself. You definitely want to check units. So in this case, we have a term L over c squared rho v squared. L would be in newtons, and then we're going to have like meters squared, kilograms per meter cubed, meters per second, quantity squared. So that's going to be kilograms, meters per second squared. Remember, F equals ma for newtons. And then we have our m squared kilograms per meter cubed, meter squared per second squared. Okay, well, I can see these cancel right away. We got a meters to the kilograms also cancel. We got a meters to the fourth over meters cubed, so we end up with a meters just in the top. Let's just rewrite that, meters over meters. Cancels, check. The other one's a Reynolds number. You can see that, mu over rho CV. So, but if we do that, kilograms per meter second over kilograms per meter cubed times meters per second. And again, that's going to check. Okay. Step 7, rewrite this. If you happen to see something in there that looks like a common dimensionless parameter like a Reynolds number, we'll have lots of Reynolds numbers, we can use this. And also remember, you can use reciprocals because a reciprocal of something non-dimensional is still non-dimensional. So L over rho v squared c squared equals a function of Reynolds number, because our rho vc over mu is a Reynolds number based on chord length and alpha. Okay, so pi 1 is your dependent variable, L over rho v squared c squared. Pi 2, first independent variable, Reynolds number, and pi 3 is alpha. Okay, sometimes we'll throw in a 1/2 right here in front because 1/2 rho v squared is a kinetic energy kind of term. All right, so stop and do questions 3 through 5. That's the method. The last thing we'll do is just a short example.